Um, so my plan today is actually to probably start from just quantum mechanics, but written in a path integral formulation. So I'm going to assume that most of you have had some exposure to quantum mechanics in some form, in one form or another. Um, so perhaps a discussion on how quantum mechanics can be formulated using path integration will make it easier to then move on to quantum field theory, which is really just a generalization. So today the plan is to discuss path integrals in quantum mechanics. And the next lecture, I think, is tomorrow. So this may change a little bit, but for now, that will probably be on QFT, but free fields. And this will include both bosons and fermions. And the next week's lecture will be about interacting QFTs. So that's the rough idea. And later we will resume lectures again with gauge theories, but for now, this is the plan. So let's start with path integrations in the quantum mechanics. Okay. Now, again, I'm going to assume that all of you are already kind of motivated to study quantum mechanics, so you are somewhat familiar with what kind of problems we want to study and what kind of things we want to compute. So I will start with some very brief recap of what the problem is that we want to solve, and then I will move on onto how to actually do the computations. So, as I said, we are starting with quantum mechanics. And particularly simple quantum mechanics at that. So it's just going to be a single particle on a line. By the way, if my audio gets cut off or if there's any problem that I'm not aware of, please write to me somewhere so that I can try to fix it. Okay. A single particle on a line. So it's just a single line. And there is some particle that's constrained to move on to this line, so it can move left and right with some potential, but it cannot leave the line. And we are going to refer to the coordinate of the line as q. And we will refer to the momentum conjugate of this position as p. So q and p are classical variables. It's just the position of this particle on this line and its momentum. Okay, and so then you may already know that the way that we describe classically, the way that we describe the state of this particle is simply by pointing out what the position and momentum of this particle are. And we may also add that in order to describe the particle completely, so we are assuming something extremely simple, so it's just a point particle. We don't have to specify anything about its size or shape or anything, but we may want to specify its mass. So it's a particle of mass m. So that's basically the only kinematical data. And then the state of the particle will be denoted by this pair of real numbers. So one for its position and another for its momentum. So the phase space of the particle. And again, recall that the phase space is just the space of all classical states. So there is a request to have my camera open. Unfortunately, my computer doesn't have the camera set up yet. And since I'm using my iPad to write, the camera position will be very strange. Um, in the future, I will try to have the meeting from my office, in which case I will have a camera, but right now I don't have a camera at home. Okay, so for the phase space, yeah, it's just a collection of all possible states. So it has coordinates, position, and momentum, and there are coordinates on T star R. So it's just some two-dimensional symplectic space. And classically, we have various observables, attributes of the particle that we may want to measure. And when I say observable, what I really mean is just functions of its position and momentum, functions of Q and P. For example, energy is an observable. And the kinetic part of the energy is simply P squared over 2m. And if it has potential energy, then the function of position, in general, it can also be a function of momentum. So it's just a function of position and momentum. And it's an example of something that is familiar, but really any function of position and momentum can be called an observable. Okay, so this is classical stuff. Now, when we quantize, what do we do? Or basically, what do we mean by quantization? I'm not going to give a rigorous definition, but roughly speaking, we replace this classical phase space by a Hilbert space. So in our particular example, this phase space was this two-dimensional space, which is really just R2, because we have two real coordinates. And we replace the classical space by a complex vector space with a limit, which we call the Hilbert space. And furthermore, we replace observables with operators on our Hilbert space. For example, so Q and P themselves are observables, right? Because Q is a function of Q and P. It's just gives you the same value as Q itself. P similarly is a function of Q and P. So these are the elementary observables, and these are replaced by operators which I will denote by hat. So they will be replaced by Q hat and P hat. And they will be required to satisfy a certain commutation relation, something like this. Okay. For more complicated observables, for example, take the product of Q and P, which is a function of Q and P. So what will these be replaced with? So here there are some ambiguities. For example, it could be Q hat P hat, but it could also be P hat Q hat. I mean, classically QP is the same as PQ, but quantum mechanically, obviously they're not. So these two things are different operators, and there's not a prior reason to choose one over the other. And in fact, you could choose some kind of combination of these things. Take any real number T, and you can say that you quantize the product of Q and P to be some number, then Q hat P hat plus 1 minus that number P hat Q hat. Right, because if you take the classical limit, so if you replace hats with unhatted things, then this just becomes QP. Yeah, because they will commute. Here, I'm simply pointing out that when we talk about quantization, we have to specify how we promote classical observables to quantum operators, because there is some ambiguity regarding ordering, and we have to choose some prescription. Okay. Now, in classical mechanics, what are the kind of questions that we're interested in? What do we want to answer? So what are the classical questions? Uh, of course, there can be many questions, but pretty much all of them boil down to something like the following: that given some initial data, so given an initial state, and classically, again, a state simply means its position at time t equals to 0 and its momentum at time t equals to 0. Given an initial state, um, what is the state at a later time t? So basically, what are q of t and p of t? Right. So these are the kind of things that we want to answer. And so how do we answer these questions? We basically solve Hamilton's equations of motion. So uh, there is some function h called the Hamiltonian, which is a function of q and p. And from it, you can write down some first order differential equations. You solve these equations, then you find q and p at any given time, given some initial condition. That's basically all of classical mechanics. So what is the analogous question in quantum mechanics? So what are the quantum questions? It's very similar. So we want to say that given some initial state, and here a state is a vector in our Hilbert space. Let's give our Hilbert space a name. Let's call it H. Not to confuse with the other H. So I will write the Hilbert space as, I will try to write it as curly H, and this is normal H. So given some initial state with some vector in our Hilbert space, so I'm sure you already know that in quantum mechanics, we cannot answer definitive questions about the state of our system or of our particles. We cannot say that this particle is definitely in the state unless it's immediately after a measurement or something. But we can ask about probabilities or probability amplitudes. So instead of asking what state the particle will be at a later time, what we ask is, given some initial state, what is the probability amplitude of transitioning to a different state at a later time? So basically, we can say something like, so you start from psi at time t equals to 0, and then at later time t, um, mm, specify some other state. Actually, yeah, so the states are just states. So it's some state from our Hilbert space. So at time t equals to 0, you pick some state and you ask what is the transition amplitude from this state to some other state at a different time. Maybe there's the time t equals capital T. So we want to compute this kind of transition amplitude from one state to another. And so let me introduce a notation for this thing. So you evolve a state with a unitary operator. And in particular, the unitary operator is e to the power minus I, then the Hamiltonian, which is a function of Q and P, right? And this Hamiltonian operator, it's a quantum lift of the classical operator. So using this kind of promotion of classical observables to quantum observables, you promote whatever classical Hamiltonian you have to a quantum operator, and then using that operator, you construct a unitary operator. So this Hamiltonian will always be, not always, but in the situations we will be interested in, this Hamiltonian will be a Hermitian operator. So its exponent with an I, this will give a unitary operator. So this is the state at a later time. Forgot to mention the time. T. So we go from 0 to t. So this is the time difference. And then you compute the overlap between this evolved state and the state that you're interested in. And that gives you the transition amplitude. So these are not the only things that we will be interested in. We can also insert really any operator that you want somewhere in between these things. So you evolve your state with this time evolution operator up to some time, then you can act with some other operator, then you can evolve again, and so on and so forth. So, but these are roughly the kind of things that we want to compute. And there are various ways of computing these things. For example, there's canonical quantization, which I believe you have been studying so far. And then there's path integral quantization, which we are going to study now. So there's a question in chat. The question is, what is t here? Is it a scalar? Yes, t is just a real number. So t is literally is time. Okay. So now let me discuss how we want to compute these things using path integration. So these things are called transition amplitudes. So transition amplitude from path integrals. All right. So let me start by assuming that I have some Hamiltonian, which is a function of position and momentum, and that has the following form. So you have the kinetic pace, so p squared over 2m, and some potential pace. This is not necessarily the most general Hamiltonian. There are various assumptions that are being made. For example, that the kinetic term only depends on momentum. There is no position dependence, and the potential only depends on position. There is no momentum dependence, and there's also no explicit time dependence. All of these conditions can be relaxed, but this is a good assumption to start with. Actually, I have to write on the orders. I think sometimes I may forget to write hats. I will try to correct it. Okay, and so the quantity that we want to compute, the transition amplitude, is like this, but slightly more specific. So we want to compute the transition amplitude from a particular position to another particular position. So what that means is that, so let Q be the eigenstate of my position operator, meaning, so Q hat, Q is Q. Okay, there are going to be too many Qs. Okay, let me write it anyway, and then let me try to demystify it. Okay, so Q hat is just the position operator. And so here, this Q is a real number. So here, this Q is not a real number. Q hat refers to the operator that acts on the Hilbert space. But this Q without any hat refers to a real number. And this state, this cat with a real number inside, this refers to a position eigenstate, meaning that if a particle is in the state, and then if you measure Q hat, you are going to observe this particular position with 100% certainty. And the transition amplitude that we want to compute is simply the amplitude for the particle to go from position Q. Let's say maybe this is better. So these are q primes. So that, okay, I don't confuse with q's. So q prime is just a particular number that refers to a particular location on this line. So maybe this is q prime. And then maybe another location is q double prime. And we want to know what is the transition amplitude that the particle goes from this point to this point within some time interval. So let's say the particle is at q prime at some time t prime, and we want to compute the amplitude that the particle goes from q prime to q double prime in time t double prime minus t prime. Okay. All right. So q prime at t equals t prime, and it goes to q double prime at t equals t double prime. So what is the transition amplitude for this process? Okay. Now, in terms of this kind of expression, so what do we want to compute? So you start from q double prime. So you start from q prime, then you evolve it using your operator, time evolution operator, which is e to the minus I Hamiltonian, and then the time difference. And then you take the overlap with the state that you're interested in, the final state. Okay. So this is what we want to compute. And we can also write it as, so q double prime at t double prime, starting from q prime at t prime. They mean exactly the same thing. That you start at this location at this time, you end up at this location at this time. What is the probability amplitude of that?
I think that's going to be a t double prime minus t prime there, IHT.
Yes, yes, absolutely. Thank you. You're right. Great. Okay. So now what we're going to do is that we are going to split this process into discrete steps. So instead of going from here to here in a smooth way, we are going to measure this transition amplitude by dividing up our time interval into smaller interval, and then asking what is the amplitude to go from one location to another in a small interval, and then we take the product. So basically, we are going to do the following. So this is, so we are going to, okay, so let me first write it, and then I'll explain it. This is where we want to end up. Let me define delta t. So we are going to split up our time interval into n+1 small pieces. So our total interval is t double prime minus t prime. And then we are going to divide it up into n+1 pieces. So each small interval is of size delta t. All right. So here what we're doing is, so we start from q prime, and then we evolve it a little bit in time. So from time t prime, we go to time t prime plus delta t. And then we insert the identity operator. And then we evolve it again. And then we insert the identity operator. So we do this n times. And finally, we evolve it one last time, and then we take the overlap. Now, of course, identity operators don't do anything. So you just get, just to be sure, there are n+1 copies of e to the power minus I h delta t here. You can forget about the identity operators. So you basically have e to the power minus I h delta t times n plus 1. And delta t is nothing but t double prime minus t prime over n plus 1. You multiply it by n plus 1, you just get the original time difference, right? So we haven't actually done anything. We have simply, by hand, inserted the identity operators a bunch of times, which is fine. But the trick is to replace these identity operators by what is called a resolution. So basically, there are many ways that you can write down the identity operator, and we are going to write it down using our position eigenstates. So what that means is that each identity operator, you can replace it by an integration over all positions, and then the position eigenstates. Okay. So this might be familiar to you from quantum mechanics, but if it is not, please let me know, then I can explain.
No,
So there is a question in
projection operator.
yes?
Yeah, it's projection.
Yeah. Well, I mean, each individual piece is a projection operator.
Right.
But then you're summing over all projection operators corresponding to the eigenvalues of an operator, an observable. So that gives you a resolution of identity. So there are some subtleties with the fact that these are continuous and you have to integrate these operators. But assuming that's not an issue, this is an identity operator. So there is another question in chat which asks, so we are assuming e to the power a plus b equals 3 to the power a times e to the power b for operators equals to b. That's right. And that identity is true as long as A and B commute. And obviously, if A and B are the same, then they do commute. All right, so I'm assuming that this kind of way of resolving the identity is familiar to you. Again, if not, please ask. So after replacing each of the identity operators with this expression, and we don't want to get mixed up with the different variables, I will give a different name to each dummy variables for each identity operator. So what we can write is that so let's gather all these integrations up at the beginning. So there are n identity operators, right? So let me write it as follows. So for each operator, I'm going to introduce a variable q. So for the first one, I will call it q1, for the next one, q2, and so on. So dqj. And then simply this. Okay. So I haven't done anything other than just replacing this expression 1 with this integral expression. And I have collected all of these integrals at the beginning, and inside we have just the states. Okay. So it just follows from this expression, right? You can always go from this to this kind of expression. But it's fun to think about what this expression means. So what we have done basically is that suppose this is our time t prime, and this is our time t double prime. So we have divided it up into smaller time intervals, where each interval is delta t. Okay. And at time t, so let's say So we have our space, one-dimensional space. Previously, I was drawing this space horizontally, but I'm drawing the same space vertically now because I'm drawing time horizontally. So this is that one-dimensional space. So at each time, you have your space. Okay. So something like this. And what we're saying is that, so we start from a position, say, q prime at time t prime, and we want to end up at q double prime. But let's look at the first term. So this is the transition amplitude for going from q prime to q1 in the time interval delta t. So in this time interval delta t, I'm going from q prime to q1, which is somewhere here. Let's say this is q1. The exact value doesn't matter because we are going to integrate over all possible values, right? And then after another delta t interval, we want to go to location q2, which may be here, let's say, and so on and so forth. So this gives you a trajectory. And this will keep going, but it will end up here. So this is for particular values of q1, q2, q3, dot, 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 qn. But of course, we're integrating over all of these q values, right? So for different choices of these variables, the path will look different. It may look like something like this. But it will always start and end at the same place because q prime and q double prime are fixed. There are no integrations over these things. But with these fixed initial and final positions, here we are basically summing over all possible paths that this particle can take to go from q prime to q double prime, right? So it can be absolutely anything as long as it has the same initial and final positions. So this picture is kind of like the pictorial version of this equation. Now, so I wrote it as an equality, and that's fine. So basically, what we're saying is that we can always compute this transition amplitude by computing these smaller amplitudes and then doing some large integrations. Okay, but one can complain that if we could compute these amplitudes, even though they're small, why can't we just directly compute this bigger amplitude for a longer time interval? I mean, what really is the difference between this and this? Well, if delta t isn't very, very, very small, so small that we can actually ignore many, many contributions in delta t, then there really is no difference. But we will be able to simplify the computation of this transition amplitude by assuming that delta t is going to be very small. So we will be interested in the limit that delta t is almost zero, basically. Now, what that means is that our total time interval, so t double prime minus t prime, this is fixed. We're not going to change this. So what we're going to change is how many intervals we divide it up into, right? So here we're saying that we're dividing it up into n+1 intervals. Okay, but now if we divide it twice as many intervals, then the size of the intervals becomes smaller. So we will be interested in this limit, which basically corresponds to that we are going to divide these paths into infinitely many intervals. And we will discuss this later, but for now, just notice that if these intervals are infinitely small, so there are many, 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 many paths, many times, so then the paths will look almost continuous, right? So now the paths are kind of jittery. So they are abrupt, they change abruptly with sharp angles. But if you divide it up into many, many pieces, then they will look like smooth paths from q prime to q double prime. Okay, we will come back to this picture later. For now, what we want to do is that we want to compute this kind of expressions when delta t is very small. So let's focus on that for now. So, but before I go into that, are there any questions? Okay, so this picture is clear. Good. All right. So now our job is to compute the transition amplitudes, let's say from Q1 to Q2 when this time is very small, okay? And then the values of this Q1 and Q2, this will, what those values are, that will depend on which amplitude we're computing. But we want to compute this generally for any Q1 and Q2. Great. And here, let's take a look back at our Hamiltonian. We were writing it as p squared over 2m plus v q, right? And again, these are operators. Okay. Now, so what can we say about this operator when our h looks like this? So here we are going to use the following formula, that for any two operators, a and b, maybe I can put hats, you can always expand it as follows. Well, if there were classical things, right, not operators, then this would just be your equations. But because they're operators and they do not necessarily commute, you have to add corrections. And the corrections look like, and there are other terms where you have high order commutators. So here, this you just have a commutator between A and B. So the next thing will be, for example, A and B, and then you take the commutator of that with A, and so on and so forth. And this will keep increasing in complexity.
Do we use the Wiles identity?
No, so this identity is called Baker
Hausdorff?
Campbell, yeah. Baker Campbell Hausdorff, or if you just Google BCH identity, you will find this. Okay. And this applies for any operators on any linear space, matrices or whatever you have. This is a very general identity. Okay,
Sir,
so yeah.
Why we ignore the higher commutator on the Hausdorff?
We don't. I mean, I'm just not writing them. They are there, and you have to consider them.
Okay.
Shouldn't
However,
there be a
notice-
plus sign in the third term? E to the power plus half commutator comma b?
Might be. You think so? Okay, maybe. I'm not 100% sure about the sign. Maybe it's plus or minus. Okay. So we want to apply this formula to this operator when it looks like this, a sum of two operators, right? So one is going to be our A and the other is going to be our B. But the nice thing about this particular Hamiltonian is that, well, okay, it's not a property of the Hamiltonian. So here, we are going to utilize the fact that this delta t is extremely small, right? So it's not just e to the power h that we are expanding. We are expanding e to the power h times delta t. So in particular, let me write it down a little bit more. So p squared over 2m delta t plus, there are factors of I as well. Let me ignore that for now. Then v delta t. So this, using this BCH formula, you would write it as p squared over 2m times e to the power v, but then you would worry about these kind of things. Commutators of, sorry, so there's a delta t, right? And then another delta t. P square over 2m commutator with v times delta t. And then I was saying that there are other higher order terms. So what do they look like? So for example, you would have p square over 2m commutator p square over 2m v. And then you
Just a
also have,
commutator.
yeah, v, and then p square over 2m, etc., right? But the main point is that, so this will be multiplied by delta t squared. This by delta t squared. Right? Okay. Actually, sorry, this is multiplied by delta t squared, and these are multiplied by the cube. So for each operator, I mean, whenever you have an operator, it is accompanied by delta t. So here we have one operator, one delta t, two operators, two delta t's, three. Okay. Now we are going to use the fact that we are really interested in this limit. We are not interested in this amplitude when delta t is large. And in this limit, all higher orders of delta t are vanishingly small relative to delta t. And using that logic, we are basically going to ignore all of these higher order commutators. So that's how we ignore higher order commutators and only focus on this part. Okay, so that's the trick. That's why we divided up this amplitude into smaller pieces like this. Okay. But of course, I mean, we have reduced the complexity in one part of the problem, right? We have made this simpler, but now we have many of the things that we have to then integrate. So the complexity has been moved to another part of the problem, but we will see how to handle that. So for now, let's just focus on this part. So what do we get after applying this BCH theorem? We have a product of two things. Actually, okay, writing the hats so many times may be a bit cumbersome. So let me use a notation. Let's say capital P is P, small p with a hat. Similarly, capital Q is small q with a hat. So from now on, I will write capital P and capital Q when I mean operators. Okay, so we have this. And again, notice that I'm ignoring all of these things wherever I have higher powers of delta t. So basically, I'm treating higher powers of delta t as 0. So you have e to the power 0, which is 1. But now, once again, I'm going to insert a copy of identity in between these two operators. And this time, I'm going to resolve it using the momentum operator. So I'm going to write, say, P1, and the integration over P1. Okay. So again, this is nothing but the identity operator. So inserting this doesn't change anything. We have the same thing as before. But after inserting this, so the reason that we inserted this, and in particular, the reason why we inserted the resolution in the momentum basis is that now we can replace this operator with just a number, because this is the momentum operator acting on a momentum eigenstate. So you can replace this operator with simply the eigenvalue. Similarly, here I'm assuming that my potential only depends on position. It doesn't depend on momentum. So this is a function of the position operator only. acting on a position eigenstate. So I can replace this whole thing with a number, where I replace this operator with the eigenvalue, right? So what you get then is that this whole thing becomes just integration of something that's just numbers. And then you are left with these inner products. Okay. So we had operators before. Now they have been replaced by their eigenvalues. And these things are also well-known quantities, right? Because we know that the overlap between position and momentum is nothing but the thing that you get when you do the Fourier transformation. You have to do some kind of normalization, and sometimes you will see 2 pi, sometimes square root of 2 pi, and sometimes nothing, but anyway. And so here, so one is the conjugate of the other, with different positions, of course. So there will be a relative sign. So you will get something like this. Okay. And since these are just numbers, there is no issue with putting both of them into the same exponents. If they were operators, you couldn't do that. I mean, you have to write these, and then again, you have to write a bunch of corrections, but they are just numbers, so they commute. But notice what this thing is. So this is position. This is position, and this is momentum. So you have p squared over 2m plus your potential energy multiplied by delta t and minus I. But this is nothing but the Hamiltonian, right? So you have e to the power minus I delta t multiplying the Hamiltonian, evaluated at position q1 and momentum p1. And then you have this factor. Okay. So this is our expression for this transition amplitude when delta t is infinitesimally small. Okay. And just to make sure that the assumption is clear, so this is an equality only when delta t goes to 0. All right. Any questions so far? So I think there are some questions in the chat. Let me check. So when a particle jumps from higher excited states to a lower state, the particle does disappear from the higher state and pop up in the lower state. In this process, how can we calculate the amplitude or realize the path? So in order to talk about excited state, you have to use eigenstates of your Hamiltonian, right? Because eigenstates of the Hamiltonian, they are labeled by energies, and then you can talk about excited states or lower energy state. But here we are talking about eigenstates of the position. So we're not saying that this is excited state or this is not excited state or anything like that. It's just the particle is changing position. You could also do this computation in a different eigenbasis, and in particular, you could do this in the energy eigenbasis. There is no change in computation. The computations are exactly the same. I mean, so if the particle jumps from one state to another, I mean, that's fine. You compute the transition amplitude. You treat Qs as energies and not as positions, basically. So there's a question about how electrons jump continuously. It cannot. Of course, if all the eigenstates are such that it is completely discrete, then obviously there is no continuous jump. Here I am assuming that the particle is free to move on this line. It can be anywhere on this line, right? That was the starting assumption. If it is in fact discrete and there are certain levels where the particle can be, then the transition amplitude will have to be from one level to another. Then you cannot do an integration over Q. You have to do a summation over the values of Q's. So you replace the integrals with sum. That's actually, in terms of computations, that's slightly easier, right? Because instead of doing integrals, you are doing summations. Well, yeah, in a quantum mechanics system, things can jump. It's not that strange, right? Are these bounded operators? Yeah, let's say they're bounded operators. Where the 2 pi comes from? So the 2 pi is just a normalization. And it's not a unique normalization. The only thing is that you have to define a Fourier transform and then you have to define an inverse Fourier transform. You just have to put numbers in those two formulas such that at the end of the day, you get one. I mean, basically, the inverse Fourier transform has to be the inverse of the Fourier transform. But here, I'm just choosing some convention. I mean, we didn't have to worry about 2 pi. In fact, I'm not going to keep track of all the normalization factors. I'm mostly going to worry about the integrands. Okay. Seems that's all the questions. Okay, then let's move on. So we have established some formula for our infinitesimal transition amplitude. But this was a little naive in the sense that, again, we assumed to make life simpler, we made some assumptions that the kinetic energy only depends on momentum and the potential energy only depends on position. In practice, this may not always be true. And if that is the case, then here you will have, for example, if your potential energy depends on both position and momentum, then you cannot just replace this with a number by acting on the state, because this will not be an eigenstate anymore. Right, this is not an eigenstate of momentum. So in those cases, we have to be a little more careful about what you end up with. And then you also have to worry a bit about operator ordering. And so to make contact with some standard conventions that are used in literature, we are going to make a slight modification to this computation. So I'm not going to go into much detail about where that comes from rigorously, but let me first mention what that is. So here, in this expression, you have the Hamiltonian written entirely in terms of Q1 and P1, where this expression looks like this. So if you look at just this expression, it is almost symmetric in Q1 and Q2. You could replace Q1 and Q2, and that just seems to be a complex conjugation type thing, right? Which here it's fine. Here you have Q2 minus Q1, almost symmetric. But this seems a bit odd. Why is it that the Hamiltonian only depends on this part? I mean, I could think of this as my state, right? That has been conjugated and then taken overlap with Q1. If that was my interpretation, then here you would end up, this part would still be the same, but here you would have Q2 and then P1. So what's going on? Why is this expression asymmetric? Again, it's because of that convention. And here there are various ways of addressing this problem. What we are going to do is that we are going to say, instead of taking this expression that we have gotten from this computation, we are going to replace this. So we're going to replace our H of Q1 and P1 with H of Q bar, or maybe Q1 bar and P1, where Q1 bar is a symmetric combination of Q1 and Q2. So it's just the average, Q1 plus Q2 over 2. So now if I replace my Hamiltonian with this expression, then it's by construction symmetry. Well, okay, so then you can complain that this is not exactly what we derived. We derived this, so what is it okay to replace this with this? The point is that in the limit that we're interested in, delta t goes to 0, this change will not make a big difference. Well, actually, it will not make any difference. But this formula will remain valid when our operators are more complicated. But again, this is not the unique way of resolving this issue, but this is one way of resolving this issue, and I think it's called Weil ordering. I'm not sure, but you may have seen something similar in canonical quantization. If not, then you don't have to worry too much about it. It will not play a big role. Okay. So once we have this expression, what we want to do is that we substitute this into our very large expression. So for each infinitesimal amplitude, we substitute this, and then we see what we get. So far, it seems like we are making our expression longer and longer, but okay, at some point it will simplify. You have to have some patience. So let's see what happens. Let's look at some of the key ingredients first. So for each infinitesimal transition amplitude, we have an integration over a momentum variable. Okay, and we have an expression with the Hamiltonian in the exponent, and we have something that looks like e to the power p times difference of adjacent q's. Okay. So looking back at this expression, so for each expression, we will have an integration over a momentum variable, dpn minus 1, and so on. And then for each expression, we will have an h, but h here was an operator. To emphasize, let me put that, because I'm not writing p and q explicitly here. But after we replace with the new expression, h will be just a function, a numeric function, not an operator. In fact, there are no operators left, right? That was the point. So what we get is that, so we already had some integrations over position variables. We still have those. But now we have a bunch of other integrations over momentum variables. Don't worry about 2 pi's. And then we have expressions like this, one for each infinitesimal interval. Again, these are just numbers, so you take product of all the exponents, then you just sum over exponents. Here we have a big sum. Okay. So again, so we have a factor of the Hamiltonian for each. So each summand here came from one infinitesimal amplitude. So we have one factor of the Hamiltonian evaluated at the jth interval, coming from here, multiplied by delta t, and one factor of p and the difference of q, again, once for each interval. But there is no delta t here, right? Because these came from this kind of overlap without any delta t. But we can take the delta t common so that it will look something like this, but then we have to divide this by delta t. Okay. Everyone's following so far? Okay, great. So some things to notice here, which that these kind of summations, this delta t is inside the exponent. Let me make it clear. So these kind of integrations you may have seen before when you studied definitions of integrals. So this is a finite sum, but recall that we are interested in the limit delta t goes to 0, which boils down to n going to infinity. So this is a sum over some variables that depend on the index. There are n of these things, and we are going to take the limit that n goes to infinity, at which point delta t goes to 0. So these are kind of the definitions that kind of defines integration from first principle. For this term, for example, you would just expect to get an integrations over dt of Hamiltonian. That's fine. What about this quantity? Well, so this is the difference between q that are neighboring, right? So one coming from jth timestamp, the other coming from j plus first timestamp, divided by the time interval. So in the limit when delta t goes to 0, this is literally the definition of the first derivative of q with respect to time, right? So the point is that once we take delta t goes to 0 limit, at which point n goes to infinity, this expression involving this sum, which now becomes an infinite sum, it reduces to an integration. So you end up with, and I will come back to what happens to this part later. Something happens to the measures of the integrations. But the integrand simplifies greatly. It simply becomes an integration over the time variable of momentum, position, and Hamiltonian. Okay, so this pj simply becomes p of t, because recall that pj was introduced for each timestamp j, so it becomes now a continuous function of time. This becomes derivative of q with respect to time, and this just h q of t, q and p. Both of them are functions of time. And the summation over time becomes an integration over time from initial time to final time. Okay. This part is more problematic. Here, instead of an infinite sum, we had infinite product. So how do we make sense of infinite products? Well, it is quite difficult to make sense of infinite products like this. There are some ways of handling this, but I am simply going to say that this becomes a well-defined measure in some cases over the space of all fields such as this. And then I'm not going to worry about what that means. I'm just going to write some kind of symbol for this. Okay, so this is something that is not particularly well-defined, and I am hiding all of the complexity in some notation. So whenever I write something like this, it means that this is a limit of this kind of expression. So where you had n plus 1 variables, n or n plus 1 variables, each variable was fine. It was just a single real variable, and it was integrated from minus infinity to plus infinity, let's say. And whatever happens to this kind of integration measures in the larger limit, that is called this thing. and the same for q. I mean, you would be perfectly right to question this, because it may very well happen that this integration doesn't converge, that it is always infinity, in which case we haven't really done anything, because transition amplitude, because it's a physical process, whatever it is, it cannot be infinite. I mean, we should be able to assign some number to the probability of a particle moving from one place to another. So if it turns out that what we have done doesn't produce a finite number, then we have done something wrong computationally. But for now, we are not really going to worry about it. And we will justify all of these kind of handling with infinite dimensional sums and products a posteriori. So based on this kind of hand-wavy and sketchy arguments, we will construct some prescriptions for computing, say, correlation functions or scattering amplitudes. And the fact that what we have done has something right will be justified by the fact that those amplitudes that we will compute can be experimentally verified. But for now, the main thing is that it kind of makes sense. It's not something entirely unfeasible. It can happen, right? And we haven't done anything particularly crazy. Okay, so we have written this transition amplitude of a particle moving from position q prime to q double prime in a time interval t double prime minus t prime as an integration like this. And so these kind of integrations are called path integrations, but what do they mean physically? The meaning of this is clear, right? This is just a completely finite product of ordinary integrations. Each ordinary integration is just over one real variable. So this thing makes sense for any value, any finite value of n. And we will take as our definition of path integration as the large n limit of this quantity. But in order to have a physical picture in mind, we will go back to this picture, that once everything was discrete, so n was finite and delta t was small but non-zero, what we were doing is that we were summing over the possible positions of the particle at different timestamps. And what we are summing was this transition amplitude from one position to the next. So this was basically a sum over all discrete paths. Okay. And so this continuum limit of this thing, we will simply visualize it as a sum over all continuous path connecting q prime and q double prime. Okay, because as I was saying, that once n is large, there are many, many intervals, and these paths kind of start to look very smooth. This statement has a caveat, but for intuition, it's fine. So let me pause here and take some questions, because this is going to be an important expression that we're going to use later on to do other things. So let's see, if there are any problems, we should address those now. I see some questions in chat. I'll try to read.
Sir, I don't understand why momentum is a function of t.
Because let's see. So let's get back to the discrete formula. Where was it? Here. Okay. So this was our actual formula. That is always true. And then we took these infinitesimal transition amplitudes. So notice that there are n+1 infinitesimal transition amplitudes. So the first one is from q prime to q1, the second one is from q1 to q2, and so on and so forth. So for each timestamp, we have a small transition amplitude, right? The one that takes you from q prime to the next one, and the one that takes you from q1 to the next one. Okay.
Yes.
So then we manipulated these infinitesimal amplitudes. So we took one and we wrote it like this. So we wrote this infinitesimal amplitude as an integration over a momentum variable, right? So this is just a single momentum variable. It's a real valued thing. It's just one real variable. You are integrating from -infinity to +infinity. Nothing strange. But you have to introduce one such variable for each infinitesimal interval. So for this interval, we have to introduce a momentum variable, which you can call P0. So for this interval, I mean, for this transition amplitude, you are again writing it as an integration over momentum, but it's a different momentum as from the one that you had here. So if this was P0, this is P1. Then for this one, you would, you would write dP2, right? So you are introducing one momentum variable for each timestamp, and in the continuum limit, it becomes a continuous function of time. That's it. So whatever confusion you have about this expression, you should always go back to this expression. This is a perfectly valid expression. And it makes complete sense. So then you see what kind of ingredients you had here. So you see that, I should probably bracket these things. Yeah, so you see that you have one momentum variable for each timestamp going from 0 to 1. You have one position variable for each timestamp going from 1 to n, sorry, 0 to n. And then the thing that you're integrating, this is a sum over all the timestamps. Then you have the momentum at that time, the difference of positions at that time, and the difference at the time, and so on. And again, you have to recall your definition of Lebesgue measure or things like, I forgot even what those are called, but your calculus classes. And that one way to define an integration of a function is to divide it into small pieces. And then you approximate the area under the curve by rectangles, and then you sum over these areas, right? So the area here is f at I times delta. So you have a sum over fi delta over I, and then take the delta goes to 0 limit, at which point this becomes integration over dx. It's exactly the same, but it's taking place for two variables, q and p. That's it. I mean, two functions of the same variable. So this part is really straightforward. I mean, all the complications are hidden here, because how do you integrate over infinitely many variables? And whether the integration will give you something finite or not, that's the tricky part. Okay. So then there's a question about the while ordering, and another question about, did we lose the Q to P1, Q1? No. Okay, so let me answer the ket question first. It's shorter. So we had these kind of kets. So we replaced those with these kind of expressions, because recall that the overlap between a position eigenstate and the momentum eigenstate is always of the form e to the power I P1 Q2 for this one. And the same thing, but with a minus sign for this one. So you can replace them with e to the power I P1 and the difference of Qs. Okay, and about the while ordering, so I didn't actually rigorously derive the while ordering. I'm simply pointing out that this expression is pretty symmetric under the exchange of Q1 and Q2, because you can think of it as either this operator acting on this ket, and then you're taking overlap with Q2, or this operator acting on Q2, and then you're taking overlap with Q1. So the way that we have derived it here is the first one, that this operator is acting on Q1, and then you're taking overlap with Q2. That gives you this expression. But this seems very asymmetric in Q1 and Q2, because only Q1 appears here in the Hamiltonian. Actually, this would also be fine. You could just keep Q1. You don't have to do this ordering. But if you do this ordering, then this integration, I mean, okay, for our particular problem, both will result in the same expression at the end of it. So, but if you have more complicated Hamiltonian where you have mixed P and Q, and then you have to worry about ordering them, then doing this kind of replacement makes more sense, because it is a symmetric expression in Q1 and Q2. But again, just to emphasize, for what we're doing, this doesn't matter. You could keep what you already had, and you would end up with the same expression. Okay, that's the end of the questions in chat. But does anyone have any other question?
Can you interpret that last integration? What does it mean? The term in the integrand.
You mean this one?
Yeah.
So far it doesn't mean anything new. I mean, we have to take it literally that it's just a product of momentum times velocity minus Hamiltonian, and that's it. I mean, it doesn't have any physical name, I think. But from here, we are going to do some extra manipulation and further simplify this expression. And then we will find something here that has a physical meaning.
Okay. Thanks.
Yeah, no problem. So let us take a 5 minutes break. If any of you have any question, you can ask in between. And yeah, let's get back in 5 minutes. All right. Okay, so now that we have this as a transition amplitude, we actually want to do some of those integrations and see what we get. But again, if you start with a completely arbitrary Hamiltonian, then you are not going to be able to simplify this any further. This is the best you can do. You cannot perform any of these integrations. But we're going to make some assumptions. Well, it's the same assumptions as before, with one added, but I will write them down anyway. H, let me think of it. Yeah, okay, so for now, let me assume some simplifying assumptions. They're not all necessary, but they will make life easier for now. Okay, so the first assumption I'm making is that H, our Hamiltonian, is quadratic in P. So the Hamiltonian that we wrote down, let's not go back too far. So the Hamiltonian that we have been working with so far, it looked like P squared over 2m. Is there a question? Maybe not. So this Hamiltonian certainly satisfies this property, right? It's quadratic in P. Let's see. And the other assumption I'm going to make is the same as before. P squared term is Q independent. So this coefficient does not depend on Q, also satisfied by this Hamiltonian. Let's see if I do okay, if I need anything else, I'll add. But for now, let's start with these things. The reason that this one in particular is very nice is that if you look at this expression, it's quite long. But I mean, for now, I mean, just think of these as just some variable P and just some variable Q and something that depends on P and Q. Now here, if you have something that has the highest power of P squared, then this starts to look like a Gaussian integration over P, and then you may hope that you can do the integration over P and end up with something that only depends on Q. Okay, but let's see what that means. I don't know if you have encountered Gaussian integrations before. I'm not going to assume that all of you have seen Gaussian integrations, so I'm going to give a quick recap of what kind of integrations we're talking about. So let's take a brief interlude. These are extremely important and ubiquitous objects. So you may very well have seen some of the things. So the simplest example is that let's say that you are integrating over the real line, and the thing that you're integrating is something like this. Okay. And we are going to further assume that a is greater than 0. So a is a real number and greater than 0. Notice for the moment that this condition is not true for this expression, because whatever h is, we have an explicit I in front. So this reality condition is not going to hold, but we will come back to that. For now, let's look at this integration. This is a convergent integration because, as you can imagine, that whenever x grows large, this grows large. So what we're integrating becomes exponentially suppressed. So it is perfectly reasonable that this integration is finite, right? And of course, you can compute this integral. And the answer is something like this. We don't have any constraint on B. B is anything. It can be complex. I'm not going to do this integration, but you can find it basically anywhere. And nowadays you can ask ChatGPT. I believe there are many ways of doing this integration, but this is a result that we're going to use. So what is going on? So if we're doing integration over x, the thing that we're integrating is quadratic in x with a linear term. So after integration, what we find is again some exponential with something quadratic, but it's quadratic in the coefficient of x in the linear term. That's the main point. And that the thing that was in the coefficient of the quadratic term still remains, but in the denominator. So it has been inverted. All right. Now, so this is fine, but the kind of integrations that we have, so even after assuming that h is quadratic in P, so maybe h is exactly this. So then here you have P squared over 2m. So quadratic, that's fine. But the coefficient is I over 2m, right? Not a real number. So we actually have to perform these kind of integrations. I a x squared plus, we may have some linear term. And it is important to keep the linear term because we have something that has P and Q. I mean, we have a linear term in P. The coefficient depends on Q. So we want to, if we want to do integration over P, we have to be able to handle linear terms in P. So that's why we're keeping a linear term. Okay, so what about this integration? The first question, of course, is this integration even convergent? We said that this integration converges because for large x, this is very small because of this positivity on A and this minus sign. But that doesn't apply anymore. Regardless of whether x is large or small, this is just a phase. So it's not even clear that this integral converges. And in general, it may very well not. But again, we are going to extract some number out of this thing. And the trick that we're going to use is the following. Instead of doing this integration, that we are not even sure that it converges, we are going to do a different integration that we are sure that it converges. Basically, all we're going to do is that we are going to replace this coefficient. It was I. I mean, we are going to keep this, but we are going to add something else. So now it's going to be I minus epsilon. Okay, for some epsilon greater than 0. So all we have done is that we have added a term here, minus epsilon a squared. Yeah, okay. So this all actually depends on what the sign of A was. So for simplicity, let's assume that it's greater than 0, because if it is less than 0, then I would choose the opposite sign for epsilon. Anyway, there's no loss of generality in this assumption. So now again, it converges because if x is large, then this minus epsilon a x squared is going to be very large. And the whole thing will be suppressed exponentially with a complex coefficient, but that doesn't matter. The whole thing is suppressed. Okay. Of course, you should complain that whether this is convergent or not is irrelevant. This is not what we want to compute. We want to compute this. So why do we care if this is convergent? Well, we can, of course, compute this and then take the limit, right? Then take the limit that epsilon goes to 0. And if you have taken any analysis class, you would still complain because limit and integral signs do not commute when the integrals are not absolutely convergent. Okay, but these are the kind of things that we do in perturbation theory. And again, the justification comes a posteriori, that the results that we get correspond to what we observe. Otherwise, this would be somewhat of a crazy thing to do. But let's see, if we do this modification, what answer do we get? Again, I'm just going to write down the answer. It's not too hard to derive. And it's actually very similar to what we had before. I think it's this one. Sure. Okay, yeah. So this is what you get after doing this computation. So now you can take epsilon going to 0 limit. We have to worry a little bit about this factor because there's a square root. So there can be some branch cut type behaviors. But at the end of the day, we are not going to worry too much about this kind of overall numerical factors. We are going to worry more about what we get as this expression. And this expression is very similar to what we had before. It's the square of the coefficient of the linear term with the coefficient of the quadratic term appearing as an inverse. Now there are some modifications because of this epsilon, which vanishes in this limit. Okay. You will find how to do these kind of integrations in many, many places. But we are going to use a particular trick for doing this computation. So let me now demonstrate what that trick is. So let me just give you the prescription. So whenever you have an integration like this, that's quadratic in the exponent, and you're doing an integration over all values of x, you can do the following. So take what you have in the exponent, okay? Then you extremize it with respect to x. You solve what you get. What you get is okay. So this is some linear equation. So there's a unique solution for x. So this is the value of x for which this is extremized, right? Now substitute this value of x into this exponent. So start with what you had. So e to the power I a x squared plus bx. And just make this replacement that x goes to this critical value. And what you will find is exactly the part of the integral that we care about. Okay, so this is the same as this. Of course, this process does not tell you what this number is, this number. That you have to figure out somehow. But again, we are not going to worry about this number because at the end of the day, when we compute things, we are going to normalize things in a way that all of these numbers will go away. This will not go away. This we have to figure out. And this is the way that we are going to figure this out. So we are going to take our integrand. We are going to extremize what's in the exponent. and then substitute the critical value back into the exponent. And that will give us the answer for the integration. If you haven't seen this before, it may seem a little strange, because what does this process have to do with this integration? Well, the intuition comes from the fact that this is going to be very hand-wavy. But the idea is that this is a phase, right? And so near a critical value of x, so near this value of x, if you vary x, the value of this function doesn't vary significantly. It varies very slowly, right? Because so you take any function, and you look at a critical point of that function. So if you vary a little bit around your critical point, the value of the function remains almost constant, right? That's the statement that the first derivative is 0. Anywhere else, where the first derivative is non-zero, the value of the function will fluctuate quite a bit. And you can kind of imagine that if you vary x, and if this fluctuates a lot, then because these are phases, so they're like sines and cosines, so they're oscillating waves. And if you have a bunch of waves that are oscillating rapidly, and then you add them up, they will mostly cancel each other, right? If it's a very highly fluctuating waves. So that's what roughly happens, that around a random point, random value of x, when you vary the values of x, this phase fluctuates rapidly, and when you add them up, those contributions cancel each other mostly. This doesn't happen near a critical point, because near a critical point, this value remains basically a constant. So now you have constructive interference. So it kind of makes sense that this integration will pick up mostly contributions from around critical points of this function. Well, this function happens to have only one critical point because it's quadratic. So it will mostly pick up contribution from that critical point. But it doesn't tell you that that is exactly what you get, right? You could still have corrections. But the beauty of this quadratic exponent is that it doesn't have correction. That is the exact answer. The value of this function at the critical point is the final answer. Okay, so that's very nice. That's the nice thing about these kind of integrations. And these are called, Gaussian integrations, and these are some complex version of it. Okay. So this is the process that we're going to follow when we want to evaluate this. So what we want to do is that we want to integrate over all values of p. Okay. Let's see. I think there's still some time. So let me make some additional comments about this limit from the finite version, the discrete version, to the continuum version. Maybe that will be helpful in understanding how to actually do these integrations. Okay, so this is going to be a small detour. Actually, maybe it doesn't have to be a detour. Let's build on what we have already been discussing about Gaussian integration. Let's stay within the Gaussian integrations. So we know how to do this integral, right? An integration over one variables. We can do this even when A is real or imaginary. There's an I. Okay, but what about if you had integration over two variables? So suppose you have dx, dy, both goes from -infinity to +infinity, and in the exponent you have some function ax squared plus bx squared plus, sorry, I want to write y squared. Well, if you have something like this, then it's nothing new, right? Because there's no mixed terms between x and y, so you can write this as a product of two integrations. One depends on x, the other for y. So this is not interesting. But it becomes interesting if you have mixed terms. So suppose you have cxy, and then you have dx plus ey. This is the most general thing that you can write down. Now it is no longer a product. But can we do this integration? Well, yes, we can do this integration. For simplicity, I'm going to write this slightly differently, but you can always go from this general form to the form that I'm going to write down now. So let me say that let's see. So I'm writing x, y as a column vector. Okay. And so this is a row vector. So this is x, y, and then here you have some matrix A. Let me write down the components, A1, 1, 1, 2, and the column vector plus some linear term. We'll put a minus sign. Omega 1 and omega 2 are just some numbers. Okay, suppose you have an integration like this. This whole thing is just a number, right? Because you can break it down. It just gives a11 x x, a11 x squared, a12 xy, a21 xy, a22 y squared, and so on and so forth. You can always write down an arbitrary quadratic function of x and y in this fashion. You just have to find the right numbers. Okay, so if you have something like this, can we do this integration? The answer is yes. Let me call this matrix A. And again, I'm simply going to write down the final answer. You can figure out how to do this, or maybe some of this can be exercises. Let's see. This is, I think, the square root. Yeah, okay. So let me write down a more general expression. So this is when we have two integration variables. Let me do it for n variables, okay? So let's introduce variables x1, x2, and dot, 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 xn. Again, by x vector, I will refer to a column vector, x1, x2, and dot, xn. And let A be an n by n matrix. Start from 1, 1, till the this is n by n. And again, omega vector is another column vector. All right. Now, suppose the integration that I want to do is that product over n variables. This means transpose. Okay. This is just a higher dimensional version of the same thing, right? This is the same as this, and this is the same as this, but for n component vectors. And this integration, again, the limits are all from negative infinity to positive infinity. This integration we can also perform.
The last one shouldn't be
with
transpose, the last x.
sorry, yes, you're right. There's no transpose in the last x. Thank you. The result of this integration is, again, there's a square root, some numbers, which we will not be too worried about. But it's good to have this in mind anyway. And then okay, so let's compare this formula with the one that we had previously. So when we had one variable, in the quadratic part, we just had a number. Now we have a matrix. And the assumption here on this matrix is that this matrix has only positive eigenvalues. I mean, analogous to this being real, it only has positive eigenvalues, and that it is invertible. Well, of course, if it only has positive eigenvalues, it is invertible. And here we had a number, now we have n numbers. That's basically it. And the final result is very similar. Here we just had this number itself, but now here we have the matrix, but for the matrix, now we have the determinant. Of course, you can think of a single number as a 1-by-1 matrix, and then this number itself is the determinant. So that's fine. And here we had one copy of pi, now we have n copies of pi. But this is the more important part. So here we had something that was quadratic in the coefficient of the linear term. And again, we have something quadratic in the coefficient of the linear term. In fact, this looks very similar to this. But the difference here was that this is now in the denominator, and here A becomes the inverse. So this is a straightforward generalization of this formula. Okay. And you could derive this formula using this procedure as well. So you take this expression, you find the critical point for all the x's. So you have to take derivatives with respect to all of the x's. And then you simply make this replacement that replace x with its critical value. And so here replace all n component of x with their critical values, and you would get this. The exact computation is perhaps slightly more elaborate, but it's the same process. Okay. Now, this is rather similar to our discrete formula, this kind of formula. Okay, so if you assume that this Hamiltonian is quadratic in P, and then if you write the quadratic terms, this will look very similar to this expression, right? Because here you had n variables, and here you had something that was quadratic and depended on all of those n variables. But that's exactly what this is. Here you have n+1 variables P, and then here in the exponent you have something that's a function of P. And if H is quadratic, then it's just quadratic in P's. So you can imagine that you can try to do that integration using the same process. So this process, you take whatever you have in the exponent, you extremize, find the critical values, substitute the critical values, and then whatever you get is the answer, right? Up to some normalization factor. So at this stage, when things are discrete, you could do that exactly. You can do exactly what I said. What's computationally more useful and will be used more often is that you can also do that here. But of course, now you have to worry a little bit about what is going on here, right? So here we had n variables, and well, here we had one variable. Here you had n variables, and I said that you have to extremize this with respect to all of those n variables. Well, now you have infinitely many variables, and you have to do the same kind of things. So how do we do that? And those are the kind of things that that go by the name of functional integrations or functional derivatives. So before I write down some formulas, let me motivate those stuff a little bit. Maybe you have already started to notice that. Okay, I'll draw anyway. So when we just had one variable x, this was some real number, a single real number. Now you can think of a single real number as a map from a point to the set of real numbers. Okay, so what I mean by that is that if you have a function, right, if you have a function from a point to the set of real numbers, then all the information there is in that function is simply what real number you get once you apply this function to this point, right? So it's just a number. I mean, even though I'm calling it a function, since the domain consists of a single point, all there is just a single real number, just like x, which is just a real number. So that's why I'm saying that you can think of a real number x as a function on a point. Very well. What about a pair of real numbers? Well, you can easily think of these as a function on the set of 2 points, right? So what is a function on the set of 2 points? All you have to tell me about this function is that what this function assigns to this point and what this function assigns to these points. And I can call that x and y. So a pair of real numbers is the same as a function on the set of 2 points. Similarly, an n component vector, so x1 dot 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 xn, is nothing but a function on the set of n points. Okay, so there are n points. Because such a function would assign a real number to each point, and there are n points, so there will be n real numbers, and that's it. So
Does this also apply to complex numbers?
Yes, absolutely. So if you replace R with complex numbers, that would give you a complex n-dimensional vector. You can replace this with anything, and this will give you an n-dimensional that thing.
Okay.
Okay. So now, if you look at this integration, I am integrating over the n components of a vector. In other words, I am integrating over all possible functions like this, right? So you could say that this integration is an integration over functions on the set of n points. Real valued, happens to be real valued in this case. And when I say that take the exponent and differentiate with respect to all of the components of x, you can think of this exponent as a function of functions. So these things are called functionals. So let me write it down. A functional is a function of functions. So what is a function? A function is something that if you provide it with an argument, it gives you a number, right? A C number. So a functional, sometimes people denote it by a square bracket. So here, in order to get a number, you have to provide it a function. So maybe a function is g, and then you get a number. Okay. We don't usually think of vectors as functionals, but as you can see, we can easily do that. I'm sorry, we don't think of usually vectors as functions, but we can easily do that. So if you have a function whose argument is a vector, you can easily think of that as a functional whose argument is a function on n points. Okay. Now this expression is a function of a vector, right? Because if I give you some x, then you can give me a number. So in the same vein, I can think of this as a function of a function on n points. So this is also a functional, but because it's discrete, it's much simpler. We don't have to talk about functional when we talk about this expression. But we can. We can think of this integration as an integration over all possible functions like this, where we're integrating a functional of such functions. And furthermore, we can take this n going to infinity, and as long as we don't make these endpoints infinitely separated, but we keep all of the endpoints, let's say, within this interval, but take n goes to infinity, then these points will become very dense, and they will coalesce into a line. Okay. So then, what happens to this vector? So we were interpreting this vector as a function that assigns to each point a real number. That interpretation remains the same, but instead of a collection of endpoints, so this collection of endpoints in the n goes to infinity limit, and I will keep in mind that there's some delta hanging out here that goes to 0, which corresponds to the separation between the points, that goes to 0. These lines coalesce and become a line. Sorry, these points coalesce and become a line. But a function that assigns to each point of the set a real number is still a function that assigns to each point of the set a real number. So now this becomes a usual function. So this f, or maybe here it was called x, there was x hat, x vector, which was a function like this. Now it simply becomes a function of one variable, where this variable refers to a point on this line, right? So the interpretation is the same. So a vector like this is an assignment of a real number to each point. There are n points. But then n goes to infinity, the separation goes to 0. These points become very dense and become a line. But x is x. It still assigns a real number to each point of this set. But now we think of it as a function on a real line. So this naturally transitions into expressions like this. So where we are now integrating our functions of one variable t. And here you have some expression that gives you a number once you plug in a function. So this is a functional. But this is just a change of interpretation. Everything else we have said about computing the integration by extremizing this exponent, that all goes through. So the way that we can perform this integration over P is you have to extremize this expression with respect to P. You find the critical value. You substitute that here. And then you're left with something that only depends on Q. And recall that Q is simply something that appears as the coefficient of the linear term. So here, for example, this omega appears as the coefficient of the linear term, and the final answer is just some expression involving these omegas. Similarly, after performing these P integrations, we will find something that is a function of the Q's. So I will write down the final answer, and then we will end today's lecture. So this is the end of the digression on Gaussian integrations. Going back to amplitudes. So the expression that we are maximizing or extremizing is PET dq dt minus h, that depends on P and T. And you integrate from T prime to double prime. Now, so here again, the derivatives, they're called functional derivatives, but at the end of the day, they're basically the same thing as the ordinary derivatives. And so maybe I will elaborate a bit more on their formal definitions in tomorrow's lecture. But for now, let me just say that if you extremize this with respect to P, so if you didn't have this integration, if there were ordinary variables, then what would you do? You would just say that, okay, this is a linear, so you take derivative, you just get dq dt. And from here, you just get the derivative of h with respect to P, whatever that is. You will now say exactly the same, only you will remove this integration. So extremize with respect to P of t, and that gives you the following expression, dq t dt minus del h del P, which is a function of P and T, equals to 0. So this is the equation that you get. Notice that it is exactly the same as the one that you would get by treating them as ordinary variables. So this will give you this will have some solution, right? So let's call it P equals to P critical, which would be a function of Q and derivatives of Q, dq dt. So now plug in this variable, this value in here. So then you get T prime, T double prime. So P critical, Q dq dt, dq dt. You already had a dq dt. And minus H, P critical, Q.
Is that H, P and T or P and Q? P and Q.
P and Q. Yes, you're right.
Sorry.
Thank you. Okay, great. Now, this expression, so once you have substituted P for its critical value, this only depends on Q and derivatives of Q. And this expression is called the Lagrangian, which depends on Q and derivatives of Q. Okay? And this transformation that takes you from this expression involving P and Q as independent variable to an expression involving only Q and derivatives of Q that you get by substituting P with its critical value, this is called the Legendre transformation. So this is called Legendre transformation. Okay. So the point is, the transition amplitudes that we were talking about, this one, so we can write it as integration over Q only, because we have done the integration over P of exponent of I, then the Lagrangian. Okay, this with the assumption that our Hamiltonian is quadratic in momentum and the coefficient of the quadratic term does not depend on position. Okay, that's it. So this is the expression that we have. This is the simplest expression that we have of this transition amplitude without specifying further about the details of things. And okay, just to remember that we have boundary conditions that we are integrating over all functions Q such that at T prime, they were Q prime, and at T double prime, they're Q double prime. So with these boundary conditions, you sum over all paths such that these boundary conditions are satisfied. And the answer is this transition amplitude. Okay. So for today, I'm going to stop here. So tomorrow, maybe I will explain a bit more about the technicalities of doing calculus with functions as opposed to single variables or discrete variables. And then we will go from quantum mechanics. Okay, recall, so all we have done so far is in the realm of quantum mechanics, right? So we had a single particle. However, notice that at the end of the day, what we have found is an integration over functions of one variable. Now, you can easily imagine generalizing this to integration over functions of multiple variables, satisfying some boundary conditions depending on some functions of those functions. And that will basically be our pathway to quantum field theory. Yeah, so that's for tomorrow. For today, that's the end of the lecture. And if you have any questions, I will try to answer some.